Hi everyone, today we're going to be talking about topic 3.9, separation of solutions and mixtures by chromatography. So we should already be pretty familiar with the concept of filtration just due to the lab that we had done a few weeks back, as well as some problems that we've worked through already. But filtration separates mixtures based on differences in particle size. Typically you use something like a filter paper in a funnel, right? And this collects large particles. And this is also based on the pore size of your filter paper. So if you have really, really large particles, like some sort of a solid, a nice fine filter paper will catch all of that solid so it doesn't go in with your liquid. One important thing is, this does not work with solutions. So if I had some sort of a salt dissolved in water, I can't just filter that to get the salt off of there. I have to get rid of it. I have to remove it using a different method. Another common technique used to separate solutions is distillation. And so distillation separates solutions and mixtures based on boiling point, or BP, right? Sometimes we'll abbreviate it. And so this can separate homogeneous mixtures and heterogeneous mixtures. So if I have, say a mixture of, for example, water, its boiling point is 100 degrees Celsius, and I have methanol, CH3OH, its boiling point is about 65 degrees Celsius. This would boil first, and then this would boil second. And so by boiling that mixture, you can boil our methanol first, our CH3OH, collect that into a different container like we're seeing over here, right? And so this is actually an example with salt water, but it's the same way. Here we have our solution or our mixture of some way, right? Heterogeneous or homogeneous. It'll start to boil, right? And so here it's a gas. Here we have cold water. And what happens is there's a tube inside of here where the solution can then condense. And the liquid now flows down this tube, and you collect your liquid here. And so whichever one boils first is what you collect first, and this is essentially a way that you can separate out either a homogeneous or heterogeneous mixture. Now, the last method of separation that we're really going to spend a lot of time on, and we should know, is known as chromatography. And so chromatography is a technique that separates compounds, in particular, I'm going to say solutes, right, because we're working in solutions, by polarity. Just as some vocabulary reminders, solute is the substance being dissolved, and the solvent is the substance that's doing the dissolving. A few other terms that'll kind of make sense on the next slide that I want to define are stationary phase, and that is the substance that remains in place during chromatography. And so this will, in some cases, be like paper. Sometimes it's a metal surface. It can be silica, which is silicon dioxide, SiO2, and we'll talk a little bit more about that in a later slide. But it's essentially the phase that does not move, right? It's stationary throughout it. You have the mobile phase, and that is the substance that moves. And this is usually the solvent, right? You can have alcohols, sometimes water is used, other organic or non-polar solvents are often used as well, and that'll be your mobile phase. And these can be both polar and non-polar, and usually we use a mixture of the two. So the most common form of chromatography that we're going to be talking about here is paper chromatography. And so if you look at this diagram on the right here, we have our paper. That is our stationary phase. And we have some sort of a solvent. This is our mobile phase. And what's going to happen is through capillary action, right, which we talked about a few lectures ago, the solvent is going to slowly travel up the paper as it's submerged in it. So what you'll do is you'll put your sample, right, of your mixture right at the bottom there. As time goes on, the mobile phase is going to move up the paper, and it'll separate your compounds based on polarity, right? And so compounds separated based on polarity, right? And so we have to remember like dissolves like. So with a non-polar mobile phase, non-polar compounds move further up the stationary phase. Which makes sense, right? If I have a really non-polar mobile phase down here, as if I have really non-polar compounds, it's going to want to move up with that non-polar phase as it's moving up the piece of paper. But if I have really polar compounds, it doesn't like that non-polar solvent, and so it's going to stay closer to the bottom. And the way we compare different compounds on a chromatography paper or on a chromatography plate is by a concept known as RF. So RF is the distance traveled by your spot, typically in centimeters, although it doesn't really matter too much, but typically in centimeters, divided by the distance traveled by your mobile phase. So as an example here, let's say I had this TLC paper, right? I mark a line where I put my little sample. I wait some amount of time, right? The solvent is going to move up. This is my solvent. It's going to move up. I wait some amount of time, and I end up stopping it here. I take it out of the solvent there. And so there is where my solvent ends. That's where my solvent started. And I should put time just so we're not confused. And my spot ended up somewhere here. And so I would take that distance in centimeters. I would take that distance, again in centimeters. Let's say this is 5 cm, and this is about, I'm going to draw this just a little bit longer, 3 cm. And so my RF, in that case, would equal the distance traveled by the spot, 3 centimeters, divided by the distance traveled by the mobile phase, 5 centimeters. So 3 over 5, you can do the calculation, right? It would be 0.6. There's a similar technique to paper chromatography that's often used in chemistry labs that's known as thin layer chromatography. And so this occurs on thin layers of plastic rather than on a sheet of paper. What happens is there's a really thin layer of silica, which is SiO2, or what's known as alumina, which is Al2O3, on top of the plastic. Both of these are highly polar. And so very polar compounds travel far on the plate, on the piece of plastic. And so these are very often used to separate mixtures in chemistry labs. Whereas the paper chromatography is most often used for dyes and a lot of biological samples. And similarly, you calculate RF to determine distance traveled by your compounds. Now, you may be also wondering, hey, Dr. Rita, like, if I'm doing this on a paper, how do I actually collect all of the compounds that I'm trying to separate using chromatography? Well, that's when column chromatography becomes a thing. And so this is on a larger scale. So rather than using a tiny amount of material on a piece of paper, you're using what's known as a column, which is this really long tube right here. You pack the tube with stationary phase, which is normally silica, which is SiO2, or alumina, which is Al2O3. And then you add your sample to the top. Right, that's what this is. This is sample addition. And then you wait some amount of time and you keep flowing solvent or mobile phase through the column. Right, and so I'll keep adding solvent, and as I'm keep adding solvent, allow the solvent to completely drip through, what will happen is your compounds start separating. Right, and so compounds separate based on polarity, similar to paper chromatography or thin layer chromatography. Now you can picture the column sort of like an upside down chromatography paper. So here I'm going to just draw a little chromatography paper. Let's say here's where it started, here's where it ended. I have a spot here, I have a spot here, and I have a spot right there. What's going to happen is that the spot on the top, this will come out first. This is going to come out second. And this spot closer to the bottom will come out third, right? Because it doesn't like the mobile phase that much. It doesn't want to travel up with the mobile phase. And so similarly here, this is just going in the opposite direction. This will come out third, this will come out second, and this will come out first. Now I wanted to loop in topic 3.10 solubility in here as well, just because there's not too much to talk about in this case, and we'll do some more practice problems together in class, but I at least wanted to throw it in here because there's only really one slide on it. The biggest thing to remember about solubility is the idea that like dissolves like, meaning polar solvents dissolve polar solutes, and similarly, nonpolar solvents dissolve nonpolar solutes. And the reason for this is because solute and solvent share similar IMFs. Right, and so a polar compound, for example, I'm going to write that down here. Right, a polar solute might have some dipole-dipole, might also have some H bonding, depending on its structure. And both of those, or it can also have ion dipole. Right, ions are pretty polar. And because it has all of those, polar solvents have the same exact kinds of IMFs, and so polar solvents like to dissolve polar solutes. Now, if we think of nonpolar, that's typically your London dispersion forces, your LDFs, and so your nonpolar solutes, which have LDFs, will like to dissolve in your nonpolar solvents, which also have LDFs. So here's just a quick little example of a practice problem. What we have here is this TLC plate. We got to remember this likely has silica, which is very polar. So we have a very, very polar stationary phase. We're told that we have a thin layer chromatogram. We have a mixture of different products. It says this separation was performed using 50% ethyl acetate in 50% hexane as a solvent, right? That's our mobile phase. If we look at our table here, hexane, we're told it has a really, really low polarity. We're told ethyl acetate has a very high polarity, right? And so our stationary phase is polar, and our mobile phase is polar and nonpolar, right? It has a polar solvent, it has a nonpolar solvent, and so nonpolar things will want to move up it, will want to move with the solvent a little bit, but polar much more so, right? Because we have a polar stationary phase and a polar mobile phase. And so it says based on the basis of this chromatogram, right? If we look at where our products are in relation to the solvent, and information about the solvents in the table, which of the following would be the best way to decrease the distance that the products travel up the plate? And so A says use pentane instead of hexane. If we look at the relative polarity of pentane and hexane, we'll see that's the same. And so if it's the same polarity, that shouldn't change anything, right? Because compounds move based on polarity. So if you switch out the solvents for one that's the same polarity, nothing is going to happen. This one says to decrease the percentage of ethyl acetate in the solvent. If we decrease our polar, then we should decrease the distance polar solutes travel. And so this would be a pretty good answer. But let's look at the other choices. C says to increase the amount of ethyl acetate. Well, if we increase the amount of ethyl acetate, we have a polar stationary phase, we have a polar mobile phase. These, if we increase ethyl acetate, or EA, the spot should go up, right? We have a more polar mobile phase now, and so these should actually move up with more ethyl acetate. And so that wouldn't make sense either, because we want to decrease the distance. The other one says we can add 5% methanol into the solvent. If we look at our polarities here, methanol is more polar. If we add a more polar solvent, it should move up the plate. So that one also doesn't make sense. And so the answer here would be B. If we decrease the percentage of ethyl acetate, see if we do 30% ethyl acetate. I'm going to actually write this in red just so I can show where the spots might show up. If we do 30% ethyl acetate, or EA, and 70% hexanes, or hexane, then our spots might look a little bit something like this, right? It should move down the plate in that case. For now, that's all I have. We'll do some more practice in class. Thanks, guys.